Hello again, everyone. Welcome to day 3 of 9495 and the second to last day of notes, really, for our class with the thinner version of this chapter. We'll do this today. You have one set of new notes on Thursday, and then most likely, I'll let you know for sure on Thursday, I would give you a quote-unquote test next Tuesday. So those looking to improve a test grade, test average, which I know is quite a few of you, you'd have that opportunity next week. But like I said, today's 9.4, the third day. Starts out, you kind of see here with the ratio test at the top, and then I start you with the tests that we've currently have done to determine if we have a series that would converge or not. The very first one that we talked about was the n-term test, that as n goes to infinity, really it's 1 and 2 are the n-term test, they kind of go together. As n goes to infinity, your limit has to exist and it has to equal 0 for a series to converge. If you have a geometric series, so this is number 3 here, if we have a geometric series, as long as our ratio has an absolute value of less than 1, we know our series will converge. We did a p series last time. The p series, if p is a 1, we get what we call the harmonic series. We know that diverges. If p is less than 1, it's going to diverge. If p is greater than 1, it's going to converge. And then I suppose actually the p series was 2 times ago. Last time we did the alternating series theorem, where as long as we had this little guy in front of it or something equivalent, that's going to go positive, negative, positive, negative. Then as long as this thing was positive, that's what this was, because as long as our general term here was positive, that guarantees with this out in front that our series would change signs every single term in the sequence. And then our a sub n needs to be a decreasing series that's going towards 0 as we calculate the limit as n goes to infinity. And if it satisfied both of those, then as an alternating series, it converged. So the last one that we are aware of, that we need to be aware of, is what's called the ratio test. So the ratio test is, here's our sigma sign, here's our general term. Let a sub n, the sum of a sub n, be a series where all terms are positive, and that you're given this little limit here. So notice what a sub n is when we look at this formula here. A sub n is the original sequence. So when we set up our limit to calculate what p is, that's what we always look for when we're doing a ratio test. The denominator is the original term that we are considering the convergence or divergence of. The numerator is whatever that term is as the n plus 1 series. So the easiest way to show this is, let's say a sub n is the harmonic series, and we're going to set up a fraction. The harmonic series we know is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So this is the first term, this is the second term, third term, fourth term, fifth term, so on and so forth. What the numerator is saying is, if this is the first term, and if n is a 1, then what we really get is a sub 2. So the first term up here would be 1/2. If n is a 2, so if this becomes a 2, then I'm looking for a sub 3 on the top. Well, a sub 3 is that 1/3. If a sub 3 is your denominator, then the third plus the first term is our fourth term, which is a 1/4. So that's what that's alluding to. This is your original series. This is the n plus 1 series. So we always go one term behind what the denominator would be. So we're basically eliminating that first term. Okay? And what the ratio test tells you, let me see if I can erase this. Why can I not find that? Found my eraser. Is that if we set up a limit of the original series as the denominator, and then the original series as the n plus 1 series in your numerator, and we then calculate the limit of that, we're going to get some sort of a value here. And again, in class, we probably spent a little more time explaining that, justifying that. If, again, you're very curious why this is, you're on YouTube, do a quick little search real quick. You can find some nice little proofs of all of this with some better diagrams than probably what you're going to see with me doing this on the computer right now. But as we set this up, as n goes to infinity, and we get this limit here, the limit we call p, if p, so if the limit of that ratio as n goes to infinity is less than 1, then you can see here we converge. If that limit is greater than 1, that series is going to diverge. And if p equals 1, that kind of stinks because that means it's insufficient information and we still don't know the answer. What that would then mean is if we were to get a p to equal a 1 when we do our ratio test, that means we've got to refer back to these guys, and then hopefully one of those would give us our answer. What happens is a lot of people really like the ratio test that we're going to do. It's the first one that you pretty much just do all the time the same exact way. And most of the time it's going to work. It's either going to give you a p greater than 1 or a p less than 1 or greater than 1. But every once in a while you get this p equaling 1, and then that prevents us from using the ratio test for every single one. Okay, so that's our ratio test. And let's do some of these. You kind of see how this plays out. So we'll start with one that I think is fairly nice as the ratio test goes. So it says determine whether the following series converge. Right now I want you to exclusively use the ratio test. So what we're going to set up is a fraction. So we're basically setting up, let me create some space here so we can see this. We're setting up this fraction up here. So we're going to take the original series, that's our denominator. So let me try to leave some room. Figured out how to make my pencil a little smaller, so hopefully I can fit some of these in here because some of these get a little ugly. So this is the original series, and the original series goes into our denominator. In the numerator, we're going to take our original series, the nth term, and do the n plus 1 term. So the numerator would become n plus 1 divided by 3 to the n plus 1. And then what we want to know is what is the limit of that ratio as n goes to infinity. So we're going to want to clean these up. So if we were to clean that up, multiply by the reciprocal of this one, so you're going to get n plus a 1 over 3 to the n plus a 1 times the reciprocal of your denominator, 3 to the n over n. A little algebra here to clean this up. So again, we're still just working on cleaning this up a little bit. I hope I can squeeze these in here today. This could be tricky for me. You'll have your n plus a 1 here, and then hopefully we understand when you see the way this is written, the reason we would be adding exponents, so I'm going to do this up here, is because, and we've talked about this in other things we've done throughout the year, the reason we would ever want to add exponents, n plus a 1, is because we had two of the same bases multiplied by each other, and that causes us to add our exponents. So we're going to rewrite this term here as a 3 to the n times a 3 to the first. And then times still the 3 to the n over n in our second one. What you will then see happen is this 3 to the n is going to cancel out that 3 to the n. So what we are then left with is the limit as n goes to infinity. We have just an n plus a 1 on the bottom, and then what we're left with in our denominator is a 3n. That then sets up pretty nicely for us to evaluate this limit. As n goes to infinity, these have the same degree, both degrees of 1, so that means their coefficients are going to be your limit. Our limit is a 1/3. So if we again look at our criteria up here, if our limit, our p, is what it's called, is less than a 1, which it is, 1/3 is less than 1, we know we are going to converge. All right, so what we would then say, similar to all the explanations we've given before, this converges. And we would now say what test we used still. In this case, we would say the ratio test. And then we would say with a p equal to 1/3, which is less than 1. That's how we could justify something if we are using the ratio test. 2, same thing. Differentiate these. Let's go out here. Our denominator is the original series. Oops, I don't know why I gave you the numerator. The numerator is our n plus 1 series. So let's simplify this again. So we get 1 over 3n plus 3 times 3n. You could factor out, reduce all those by 3's. Unnecessary. We're going to be able to make a conclusion out of this right now, sort of anyway, because we can calculate this limit pretty easily. Degrees are the same. They're both 1s. We look at their coefficients, 3 over 3. That would equal a 1. If P equals a 1, what that means is the ratio test doesn't work. We don't have enough information. It's inconclusive. What that would then mean is we would need to look at this series and come up with one of these as an alternative to determine if this is a convergent or a divergent series. So the way that I would approach this, pull out that 1/3 so that's a little more obvious. All you would then be left with is a 1 over n as your series if I rewrote the original. And then what we should know then right away is that this is going to diverge because it's the harmonic series. And we know the harmonic series diverges. All right, so the ratio test will not always work right now. Really, for number 2 in the future, or actually when we just go to the next page, when they're all kind of mixed together again, if you can recognize that's a harmonic, just go right to the harmonic very quickly. All right, 3, I'm going to make this big because I really want to try to squeeze this in with my pen. All right, is the n factorial multiplied by your 2n factorial. We showed last time that this passed the nth term test, that a coefficient of 2n outgrows 2 separate n factorials. So that if you, again, want to show that, I think I showed it on the calculator just with numbers, how that worked. You can go back and look at that. We're going to go ahead and do the ratio test here. We know it passes the n-term test, and we know we need to consider other options because the n-term test only proves if it diverges. So with this one, we try to make this clear. You're going to do the original series in your denominator, and then your n plus 1 series in your numerator. So we're going to have n plus 1 factorial times n plus 1 factorial. All of that gets divided by the n plus 1 here, so that would get written as 2 times an n plus a 1. Close all of that, then we're going to have a factorial. So we always have to do the plus 1 to our n and only, and then whatever happens around it we'll simplify in the next step. So what we would then have right now is, let's go ahead and multiply by the reciprocal as I do this. We're going to have an n plus a 1 factorial and an n plus a 1 factorial divided by 2n plus 2 factorial. Take this, multiply by the reciprocal, so times 2n factorial over n factorial over n factorial. And then we want to clean this up. What I'm going to show you now isn't necessarily this problem. In a way it is, but just understand this. Let's say I gave you n plus 3 factorial. Let's not even do that just yet. So just consider n plus 3 factorial for right now. Understand what that would mean is happening if we understand what a factorial is, which I think we all do. That you would go 7 times 6 times 5, 4, 3, 2, 1. Once we get down to the 1, our factorial value is going to end. Well, if it's a variable, where do we stop? Because this should be n plus a 3, and then I would subtract 1 to get an n plus a 2. Right? I'm decreasing by 1 every single time. Then I would get an n plus a 1, then I would get an n, and then I would get n minus 1. Where would this ever stop? We wouldn't know. So what I would do is just put a factorial behind this saying, yeah, this right now, without knowing what n is, because if n is 500, all of these terms are going to appear. So at any point in time, I don't have to do all of these necessarily. If I just put a factorial behind it, this tells me that I would also, if I wanted to, have to do n minus 4, n minus 5. But again, we don't know really where to stop with those. So really at any point in time, I could have stopped this anytime I wanted. So I really could have stopped it right here. And as long as I put a factorial behind this, that does tell us that, yeah, this could continue again forever and ever and ever. But by putting this here, that's acknowledging that this does continue by subtracting 1 forever, all right, if we're just considering a variable. So now think about if I have an n factorial in our denominator, if we're going to divide this, same thing would happen here. So now let's make this a fraction. Well, I would have an n factorial, but wouldn't the next one have to be n minus a 1, and then I'd have to subtract 2, and then I'd have to subtract 3. Well, this would also go on forever. So I'll think back to the one on the top. Oops, here we go again. Come on. So think about the one on the top. That with that factorial right there, try to erase again without screwing this up. Get rid of that. This would go on forever. Well, they both go on forever, right? So this goes on forever, and this goes on forever. Well, eventually, wouldn't, like this in factorials, we did that. Wouldn't these guys cancel? The n minus 1s would cancel. Wouldn't every term then cancel that goes on forever and ever and ever? So you want to understand that to a certain extent so that we can simplify these a little bit easier. So here's how this would now get simplified. So let me get rid of all of these. One more. Is what I'm going to do is I'm only going to take the numerator and I'm just going to reduce this as far down to where it would reduce with what I have in my denominator. So notice my denominator has an n factorial here. Well, this guy and this guy both give us the n minus 1, n minus 2, n minus 3. So once I get to this n factorial, I'm going to stop so that it would cancel this n factorial, and every term after that would also have to be getting canceled. And all we would be left with is n plus 1, n plus 2, n plus 3, n plus 2, n plus 1. That's how we're going to have to simplify our factorials. So what that means with respect to this problem move this down. That now relates to hours. So let's take this. Bring it down here. If you notice, we have an n plus a 1 factorial right here. So that technically really is n plus 1 times n minus 1, n minus 2, n minus 3 forever if we don't know what our variable is. But if you look in your denominator, notice how there's an n factorial. That also would give you an n minus 1, n minus 2, n minus 3, n minus 4, so on and so forth, forever and ever. So all we're going to do is reduce that down far enough to where it would cancel out the n factorial. That's going to look like this. So this n plus 1 factorial, all I really need to do is do n plus a 1, n, and then I'm going to put the factorial behind that, indicating that we would go on forever. And the reason I'm stopping there is because I would have had this n factorial in my denominator, and then all terms, including your n and n minus 1, n minus 2, all the terms following n would cancel at that step. So then these two would cancel. I'm going to do the same thing with this one. That one, hopefully I can extend this enough. I'm going to do another n plus a 1 times an n factorial, and I'm going to stop that one at n factorial because I also have an n factorial here. So I'm going to do that one to n factorial, and then these guys cancel each other out. Same thing with my 2n plus 2 factorial. So think about what this would be. This would be a 2n plus 2, 2n plus a 1, 2n, 2n minus 1 forever and ever and ever. So the factorial behind it tells us the whole forever, forever, and ever part. Well, if you look at your numerator, notice how we have a 2n factorial. So what I'm going to do, I'm going to stop without having to put this term down, and let's put the factorial behind that one. that would then take this 2n factorial, make it look like this 2n factorial so that they can cancel. So I'm going to take this guy here, and I'm going to write that as 2n plus 2, 2n plus a 1, 2n, and then instead of continuing on, I'm going to effectively go on by just putting the factorial here, and that is because I have a 2n factorial in the numerator as well. So then this would cancel out that, and all the terms behind those would also be canceling out. So what we ultimately then end up with is, actually we can do one more little reducing here. So a lot of this is gone. Look at what's left over. We have this guy, and in the numerator we have an n plus a 1 and an n plus a 1. Well, if you look at this guy would reduce down, we can pull out a 2 to 2 times n plus a 1. So that then this n plus 1 would cancel out that n plus 1. And after all of that, if the only thing we left have in our numerator is an n plus a 1, in our denominator we have a 2 times a 2n plus a 1. So all that reduces down to something that makes our limit nice and easy to evaluate. Degrees of 1 on top. The coefficient on the top would be a 1. If we were to distribute here, the coefficient in our denominator is a 4. P series again. If our P is less than a 1, we're going to converge. And that's what just happened here. So this we would say converges. It's a P series. What am I talking about? Ratio test. Sorry about that. So ratio test with our P equal to 1/4, which is less than 1. And that's how we know it converges. That's your ratio test. So now on this next page, we just got a handful of problems where it's whatever test we've done up until this point, can we recognize it? All the ones that are in play from before, those 5 that we mentioned at the beginning, and then now the ratio tests are all options. So it says using any test, determine if we converge or diverge. You're going to basically state the test that proves no matter what. I don't know why I just have it if it diverges. You're going to state either way, whether it converges or diverges, you're going to state your test. All of these, again, haven't talked about it yet, but the nth term test is always the first thing that you're going to deal with is the nth term test. It should say term test. So that means with every one of these, as n goes to infinity, this better equal 0. And if it doesn't, then it fails immediately. We don't have to worry about any of our other tests. So with this problem, this is actually a nice one. Remember what this simplifies to be, 1 plus 1 over n. What this limit is, if we apply this limit to this problem, this is our e to the first power. So since that does not equal 0, this fails our nth term test, which is nice. That means right away we diverge. We would then say nth term test. The limit as n goes to infinity for our general term is e, and not 0 like it is supposed to be. All right, number 5, you've got a couple of options. I'm going to show you both. I think the easiest way is right away we hopefully, first do your nth term test. As n goes to infinity, our faster growing function is in our denominator. So this does, in fact, pass the nth term test. So in some ways that's unfortunate because that just means we have to continue on. Nth term test, again, is only for divergence. It doesn't confirm that we converge. It just tells us that we would diverge. So the fact that it passes the nth term test doesn't mean anything other than we need to continue on. What hopefully is easy is that we can look at this, hopefully at this point, and say that this converges. We would hopefully recognize this as a geometric series with a ratio whose absolute value is equal to 1/3, which is less than 1. We also now could do the ratio test here. Also valid. Let me rewrite this. So we would take the original series in our denominator. Actually, at this point, at some point, we graduate to where we don't have to write that out every time with it in our denominator. Everybody, I think, pretty bright people know that we could do our n+1 series, and instead of dividing by the original, we would just multiply by the reciprocal. Here we go. So that's our reciprocal. We now would have 2 times 3 to the n in the numerator. Remember our little algebra here. 3 to the n times 3 to the first, how that would simplify to be. And then our 2 in our denominator. When we simplify this, the 2's are going to cancel. The 3 to the n's are going to cancel. All we're going to end up with is a 1/3. And then we know the limit as n goes to infinity for any constant is that constant. That's our 1/3. So we would also be able to say this converges for the ratio test with our p-value equaling 1/3, which is less than 1. This is the quickest. I think geometric series most people understand. That's what I would probably recommend, but we could also do the ratio test. 6, again, got to pass the n-term test. As n goes to infinity, we hopefully understand factorials grow faster than exponentials. So this limit is infinity. So we can conclude very quickly that this diverges. N-term test, the limit as n goes to infinity of that general term is infinity, and then not 0 that it's supposed to be. 7, this, as we do the n-term test, these pass the n-term test, but this should diverge right away because this guy is the harmonic series. Recognize this is a p-series, so this would converge, but what this is doing, this is going to infinity. So even though I think this might converge to 1, I think, if we actually did the work for that, well, all that just means is we're still going to infinity, but instead of just a regular harmonic, it's the harmonic decreased by 1. But overall, we'd still have a sum that's getting bigger and bigger, getting larger and larger and larger and larger. So if we have a sum or a difference, if one of them is going to have an infinite sum, which the harmonic series does, then the whole thing is still going to diverge. 8, n-term test first. So as n goes to infinity, this passes the n-term test. That would definitely go to 0. So passes the n-term test. That just means we got to consider some other things. I'm going to first rewrite this so it's easier to see. And then hopefully we would recognize that what this is a series that right away would converge. You could do the ratio test if you really wanted to. But this is what we would call a p-series with correction. So this is one of the things we want to be careful of, and I just made the mistake myself. We now have 2 p's. One is for the ratio test. One is called a p-series. Don't ask me why they use p's for all of them. But the ratio test, if p is less than 1, you converge. This is a p-series where you just have any number over your variable to an exponent. And our p is equal to 2/3. But in a p-series, that tells us that our series diverges. Sorry. So keep those straight. As you can see, I just screwed it up. So it diverges because it's a p-series with this p, the p for the p-series, equal to 2/3, which is less than 1. So a p-series less than 1 is bad. It's going to diverge. In a ratio test, your p-value that's less than 1, you would say that it converges. So keep them straight. You can see I just messed it up. It's an easy thing to get confused. 9, a couple alternating ones coming up. So here's an alternating term. So as long as this stays positive, so if you think about what n's you're going to plug in, you plug in a 1, a 2, a 3, this term definitely going to remain positive. The only thing this then has to do is this part of our series has to have a limit of 0, has to decrease towards 0. So what we should recognize then is that this would diverge, and it's because this doesn't go to 0. All right, that would be going to 1. However, the way we explain this, we actually could talk about how this fails the n-term test. As n goes to infinity, this guy actually has a limit of 1. What the heck? Has a limit of 1. We're bouncing back and forth then if we're going to be positive, negative, positive, negative, positive, negative. Think about graphically when we graph them. We're going to be bouncing back and forth between positive 1, negative 1, positive 1, negative 1, so on and so forth. So overall then, this limit we would say does not exist. This goes to 1, but the fact that we're alternating just bounces back and forth. So this would diverge n-term test. Limit as n goes to infinity for these terms does not exist. 10, not alternating. We're just going to do first our n-term test. So as n goes to infinity, our faster growing function, n factorial, does grow faster than e to the n. So this does go to 0. So it passes the n-term test. That just means we need to continue on and figure out a way to determine if it actually does converge. If you look at it, this has a geometric look to it, but a factorial is definitely not geometric. It's not a p-series. So what this one probably ends up being, a pass the n-term test, is our ratio test. So this is a nice one to use our ratio test for. So when we set up our ratio, we're going to do the original series in our denominator. So we take our n plus a 1 series. Hold on. And then we would divide it by the original, which is really doing the reciprocal of the original. Understand how these now simplify, hopefully. We have e to the n times the e to the first in our numerator. And then this n plus a 1 factorial, this technically would go on forever. We could say that just continues to subtract 1. But if you recognize you have an n factorial here, we're only going to take that n plus a 1 and stop at n and put the factorial behind it, because every term after this n factorial would cancel out with every term after this n factorial. So these guys just overall cancel. These e to the n's are going to cancel. What we are left with on top is an e, and in your denominator is n plus a 1. Calculate the limit of this in the p-series. I'm sorry, in the ratio test as n goes to infinity. E is a constant. Don't think of that as a function. That's a number. It's 2.7-ish divided by n factorial. So this does, in fact, have a limit of 0. So we would say that this converges due to the ratio test. With a p-value equal to 0, which is less than 1. 11 looks like maybe a misprint, because if you look at number 11 and number 10, almost identical, except this one is alternating. So I wanted to do that just so we can remember the alternating idea, that the only thing that has to happen, as long as we have this little, what should be the alternating term, this term here has to be positive. So if I start plugging in 1, 2, 3, 4, 5, this is definitely going to be positive. The only thing that has to happen if it's alternating, it's a little easier conclusion to make, is that this has to decrease towards 0. And it does. Factorial is in your denominator. That's going to outgrow the exponential function in your numerator. So with this one, we could have concluded this one converges right away. And we could just say the alternating series theorem. So the alternating series theorem allows us, if it's alternating, it's got to be alternating. It's a little bit easier to say something converges. Our requirements are less. Okay, 12, I'm going to make this nice and large so I can fit all of this in here. This, got a lot of stuff. N factorial squared times 3 to the n over 2n plus 1 factorial. We talked about this in the previous set of notes. As n goes to infinity, a coefficient in front of our factorial outgrows or grows faster than a factorial to a power. So in regards to the nth term test, this does go to 0. If you don't believe me, again, you can graph that on the calculator, look at your table. You'll see your denominator definitely grows faster. So pretty much this is a simple one. Whenever you have factorials, you're almost always going to be doing the ratio test. If it passes the nth term test, that is, there's not a lot of other ways. It's not going to be geometric. It's not a p-series. All of our other options don't really work so well. So almost always going to be a ratio test. So set that up. You're going to take your n plus 1 series. So we would have n plus 1 factorial squared. So we do another n plus 1 factorial. So that's this guy with an n plus 1 term. And then 3 to the n plus a 1. All over your denominator, which is an n plus 1 series. So that would become 2, and then an n plus a 1, and then plus a 1. All of that has a factorial behind it. And then we've got to multiply, where we would divide by the original, which is really the same as multiplying by the reciprocal of the original. So this here is just the reciprocal of the original function. It's the same as dividing it by the original a sub n term. We then need to simplify that. So this n plus 1 factorial, we are going to stop that at the n and put the factorial behind it, indicating we go on forever. And the reason we do that is we had an n factorial in this other denominator that those will cancel out with. Same with this one. We're going to do an n plus a 1 and then stop at n factorial because we had another n factorial in the other denominator. And then we have a 3 here. This is a 3 to the n times a 3 when we simplify that. And then down here, this should be an n. I don't know, I have a 3 squared here. We have our 3 to the n that we had in our original problem. Think about what this is now. This is really, if we distribute 2n plus 2 plus a 1. So that's really a 2n plus a 3 factorial. And then over here, you would have a 2n plus a 1 factorial. So I'm not going to quite start canceling things out just yet. So rewrite this numerator. And then we have our 2n plus a 1 factorial in the second fraction. And then we would have an n factorial, 3 to the n. So I'm now going to simplify this guy here. I only need to take this down so that it would reduce with this one over here. So see how this is a 2n plus a 1. So we're going to take that 2n plus a 3, do 2n plus 3, 2n plus 2, 2n plus a 1, and then there's no need to do a 2n minus a 1. We're just going to put the factorial behind it, because from this point on, every term in this one would cancel out with every term in that one, so overall those cancel. We'll also take this time to cancel out the n factorials, and then these n factorials are going to cancel. Should have been a 3n right here. This 3n is going to cancel out that 3n. We would have here, let's not even bother with that. Let's go ahead and simplify this now. So bring this up here. We have an n plus a 1 times an n plus a 1 times a 3. So we have 3 times an n plus a 1 squared. In our denominator, we have a 2n plus 3 times a 2n plus 2. Let's go ahead and simplify that just so it's clear. You have a 3 times an n plus a 1 squared. And then our denominator, if we were to FOIL this, so distribute, and then the 3 distribute, we would get 4n squared plus 4 and 6, 10n plus 6. Calculate our limit. So now as n goes to infinity, same degree on top, same degree on the bottom. So look at their coefficients. Our coefficients are 3/4, so that is our limit. This converges due to the ratio test with a p equal to 3/4, which is less than 1 for the ratio test. That means we converge. Interesting stuff there. So hopefully you're following along. Hopefully that makes some sense. There usually are a number of questions when we're going through this, some clarification things. Hopefully that would make some sense as you look through that. 13, same thing I did up above with 10 and 11. Exact same problem, but we just now have the alternating idea. And what this allows us to do, the alternating idea is nice. We can look at this and say right away that this converges, because this expression here will always be positive, and our faster growing function is in our denominator, so we go to 0. So this converges because of the alternating series theorem. So if it fails the nth term test, that's nice because you're done very quickly. If it's an alternating, so if you have this little expression here or something similar, that would tell us that we're going to bounce back and forth. Alternating series also can be handled pretty quickly. So those are all the tests you're responsible for. The next thing we do on Thursday is a little different. So we'll see. Sometimes that's a 2-day. I really have to look and see how much of that topic I need to teach. So we'll definitely do that Thursday. If I think we've got everything we need to cover on Thursday, we probably test next Tuesday. And if we spend 2 days on that next section, then obviously you would test on the following Thursday. Okay, so I'll be clear about that on Thursday. I'll let you know. If you look, here are some problems you could try in the textbook if you had that. A lot of these are ratio test problems, so you get comfortable doing the whole n+1, all that good stuff. All right, because when you look at number 12, especially, easy to get lost with all of that. So good luck. Hopefully everything goes reasonably well. Reach out to me, ask me any questions, and hopefully I can explain it to you so that you can understand. Have a good night.